We need a note taker for the class. So if you're interested in doing that, I believe you can be reimbursed $25 per credit. So I don't know if that applies to the 3-hour lecture or the 4-hour total class, but you can make some money if you have good handwriting, take good notes. If you're interested in that opportunity, please come see me after class, and we can work that out. For next week, I have decided to try to make it as fair as possible for recitation, which means no recitation for anybody, since Monday there's no school. And what we're going to do instead is do a take-home quiz, which will be available on Blackboard starting on Tuesday. I'm going to try to get it up by Tuesday, and it'll be due on Friday. It's the honors code. You're going to work independently on this, and I will trust you to do so. Okay? All right. Does anybody have any questions or concerns about whatever? Are we good so far? Life is still good? Maybe not life, but at least this class. This class is okay? All right. So just in case you didn't notice, I already have up on Blackboard. I didn't post anything in the announcements. I just went straight to your assignments. So your assignment for today was up, but also your assignment for Wednesday has been up since last Wednesday, right? So just make sure that you're keeping an eye on Blackboard for everything. Check frequently. If you don't have it set up to like email you automatically when updates are there, I think you can do that. So you might want to look into that as well. Okie dokes. So let me do this really fast because I promised I would update my roster. So I want to make sure that everybody is here who should be here. So all right, Ahmed? Ahmed? No? Anthony? Kaiser, Rutger, Adam, Jackson, Jan, Ankita, Elena, Yumeng, Bethany, Teddy, Payun, George, Taylor, Annabelle, Moises, Daniel, Kyle, Sarah, Taylor, McLean, Matthew, Lauren, Penny, Taylor. Oh, there's 2 Taylors. Okay, but you guys are keeping up with that, right? Okay. Scott, Ryan, Horatio, Frank. Yep, here, okay. Adidas. No. Okay. Shelly. Eiley? No. David. Q. Cool. I think the other David is not here, right? I didn't call another David first this time. Anyways, Justin. Anna? Oh, you almost got absent. Okay, Nathan? Here. Jonathan? Here. Darren? Ruby? Here. Taylor? Here. There are 3 Taylors. Philip? Susan? Here. Miranda? Here. Wait, did I hear Susan was a male voice? Yeah. What just happened? Did we get... Oh, okay. Miranda? Renee, Dakota, was that a here? Yeah, okay. Rashay, Lou, Jessica, Madeline, Ashley, Joseph, Caesar. Oh, what should you guys be doing while I'm doing this? Yeah, great. Caesar, Harrison, Nayeli, haha. Caught myself. Courtney. Jafu. Maxwell. Ariane. Katya. Christopher. Super duper. Okay. Okay, so, and your homework is in the middle? Every day. Just do it automatically. Don't wait for me to say it. You still see? Yep. Cool. All right, so today we are going to continue our conversation about division. So hopefully what we're starting with today will be old news. You guys are now experts. So let's just make sure that's the case. Okay? So if we have a car traveling at a constant speed, okay, and it travels 1,829 feet in 19 seconds, how many feet did it travel in each second? So I want you to bust out some bars and address that question. Everybody has the question? Did you start this way? Yeah? Okay. Take a few more moments if you're still thinking. Something I wasn't able to do in time for today, but I will have by Wednesday, is a list of your names in random order for me to call on you, right? I want everybody to participate, and I feel like that's the best way to get everybody involved. With two messages, right? One is to keep you honest and attentive in class, but the other is to help you realize that it's not that big of a deal to talk in front of your peers, right? We're all in this together. So starting on Wednesday, I will have that list. In the meantime, I will still count on you for your willing participation, okay? So would somebody like to tell me what they did first? Yes, ma'am. You split the smaller bar into 19 pieces. So why? Okay, so if we're interested in how many feet were traveled in 1 second, then it stands to reason that we should mark off 1 second, right? So if I do that, how much, you sort of addressed this, so how much is this 1 second of the whole bar? 1/19th, okay, so that is 1/19th, there's a 1 there, of 19 seconds, right? So then if I'm trying to figure out how much distance is covered in 1 second,
how can I take this line of reasoning to the next level? Yes, sir.
I would do the same thing with the top, dividing the 19 sections.
Okay, so divide the top bar into 19 equal sections. I'm not going to do that because we'll be here until the end of class. But so this portion right here is how much of the whole? So this is 1/19 of 1,829 feet. My handwriting's already a little better. Aren't you guys impressed? I'm impressed. Okay, it's still not great. Still looks like I'm in second grade, but we'll get there. Okay, so are we done? What's the answer to my question? What was my question? How many feet are traveled in 1 second? Yes, sir.
Multiply, or you can divide 1,829 by 19.
Okay, so we can do division, right? So 1/19 of 1,829 feet gives you the amount of feet traveled in 1 second, right? So the operation that we performed was division, right? Oh, look at how good I did. Okay, sorry. That was really exciting. I forgot that was there. Beautiful. Okay. Look at all of that. I didn't even have to write. Okay, so the car traveled 1,829 divided by 19 feet per second. Did anybody compute that number? All right. 96.26, we'll say 96.3 feet per second. Okay? So in order to get that, though, we did distance divided by time, right? So that is speed. That's how you compute speed, right? So if you were ever wondering, this is one way to think about it, right? Now, 96.3 came out of doing division, right? So it is, in fact, a quotient, right? That number itself is a quotient. How can you think of it as a relative size? So take a moment to think about that with a neighbor. So 96.3 is the size of what quantity relative to what other quantity? Take a second, think about it, talk to your neighbor if you want to. So while you're thinking about it, keep talking and answer this second question. If 96.3 is a quotient, how can it be thought of as measuring one quantity in the units of another quantity? So answer both questions. Think about how they're the same, how they're different. Okay, who wants to take a stab at it? So 96.3, how can it be thought of as relative size? Yes, sir.
I would word it as 96.3 related to 1, the same way 1829 is related to 19.
Okay. What happened to the quantities in there? So what quantities are you describing when you use those numbers?
96 feet per second in 1829 for 19 seconds.
Okay, so you're concentrating on speed when you do that. So so when we talk about relative size, we're talking about one quantity relative to a second quantity. When you talk about speed in that fashion, we're only describing one thing. So can we try again? Yeah.
Can you say that for every increase in seconds, we have we increase by a factor of 96.3 in distance?
Okay, so I'm liking where you went with that last phrase, in distance. Okay, so what are we measuring? What quantity are we measuring relative to another quantity? Yes. So we're measuring distance relative to time. Does that resonate? Okay, so when we talk about this 96.3 as a relative size, it is the amount of distance relative to number of seconds, right? Okay, what about using 96.3 as measuring one quantity in the units of another? Yes, sir.
It represents the change in quantity with equal change in another.
Okay, can you be specific?
So like 96.3 would be the change in distance with every equal change in time.
Okay, so for every 1 second change in time, there's 96.3 feet
Yeah.
change in distance. Okay, how is that measuring one quantity in another? So I'm being really picky about the wording here, right? So you guys are giving me phrases that do make sense, okay, but we're not being specific yet. How are you measuring one quantity in terms of another? Yes. Okay. You want to take a stab?
We're defining how far something went by how long it took to get there.
Okay. So instead of using the word defining, you can use the word measuring, right? We are measuring distance in units of time. Does that sound weird?
Yes.
It does, right? It should. That sounds weird because we're trying to stretch our brains a little bit here, right? But what are we doing, right? For every 1 second, there you travel 96.3 feet, right? So you can measure how far you have traveled by measuring how long you have been traveling. Yes? Does that make sense now? A little less weird. Yay or nay? We can keep talking. Yeah.
For me, it feels like you're trying to say, like, I traveled for 5 seconds, but that doesn't give you enough information. Like, you have to say, at this rate.
Ah.
There needs more, like, you can't say one statement. Like, you have to have the rate in there as well.
Absolutely agree. Okay. So when we are saying that we are measuring distance in units of time, we are discussing this particular scenario, right? So I've got 96.3 is the quotient that I'm trying to describe as measuring one quantity in the units of another. So I've got 96.3 feet per second, right? So for every 1 second, I travel 96.3 feet. Okay, that's what we're capturing here. Okay. So if I were to travel for 3 seconds, how far would you travel in distance? 96.3 times 3, right? So in that regard, you really can measure distance traveled in units of time. You tell me the time, I can tell you the distance. Okay? All right. Okay. We're going to do one more. Okay. So plane traveled 4,012 feet in 0.002 seconds. How far would it travel in 1 second? Yes, sir.
2,006,000?
Okay, so you gave me an answer. How did you get there?
Oh, I just, it's basically just multiply it by 1,000 and then cut it in half because it's 2,000 for the second.
Okay, so you're giving me a procedure. I want to know some representations. I want some way that you can show me this visually and support it with that type of explanation. So.
I would take the small bar
Okay.
at the bottom and have it represent 1.002 second bar.
So you want the whole bottom bar to be 0.002 seconds?
For representative purposes.
Okay.
Because then you could take the top bar and divide that equally into 500 parts. Yeah, but if you take the top bar into 500 parts and you say that each one of those bars is representative of one of those seconds, like that bottom bar correlates of 1.002 seconds to 4,012 feet. And so each of the 500 bars that you have on the top is representative of one 4,012 bar.
Okay. So here's what I think I'm hearing. So if I let this bottom bar be 0.002 seconds,
Yeah.
then the top bar will be 4,012 feet, right? No? Okay.
You know how you do the thing with the lines and you have the dots connecting each of the
Yep.
lines? Do that, but make that line like way over there.
Way
and
over,
then that
little teeny
corresponds
tiny
to
over
the
here.
very end of that.
So that's what I'm saying. The top bar is split into 500 parts.
Oh, so you only want to split the top bar and not the bottom bar too?
Yeah.
And you want to have like the dotted line go all the way over there.
Basically, yeah. Because each one of those little itty bitty fractions of the top bar is one bottom bar.
So, but then if I want to represent 1 second,
That is 1 second because 1.002 seconds is 1/500 of a second.
so then to get a 1 second bar,
That's the top bar. Top bar is 1 second.
but the top, you just told me the top that this was feet. This is 4,012 feet.
That one line.
Oh.
Yeah. Okay.
So I would have the seconds on the top bar and on the bottom bar be 4,012 feet.
Okay.
And then hypothetically divide the second bar into 5 different points. So that little thing hash mark you made, that distance there would be 0.00.
Okay, so you want this to be 0.002 seconds.
Yeah.
And this whole bar is 1 second. Okay. But then what's happening on the bottom?
That would be the feet to the side.
So is this 4,012 feet? We don't know what this is, right? Because we're trying to find out how many feet correspond to one total second, right? So the whole top bar should correspond to the whole bottom bar. Okay? Is this weirding people out to have the time on the top and the distance on the bottom? Okay, so I would like to point out, it doesn't actually matter, right? It's just a matter of perception, okay? But if it makes you more comfortable, we can still keep time on the bottom. So, okay, so here's 0.002 seconds. The whole thing is 1 second. Do we know how long the top bar is? No. We don't know. That is the question, right? But I do know what? Question.
We had a similar question on homework,
Mm-hmm.
and instead of going and dividing it by 200 little pieces or however many 500 little pieces, in my, not in my head, but I just moved the decimals on each one. So then I had 2 seconds, and that would be quite a bit of feet, a lot.
It would.
And then I just divided instead of multiply. Would that be, is that a step that I should be showing that wouldn't be showable here, so I would have to do it this way?
It's definitely circumventing the issue at hand, right? So I wanted to do this example specifically because of the decimal, right? Having this decimal here can be like difficult to think about, right? I get that. That's why we're doing it. Yes, sir.
So, starting with the bottom bar,
Uh-huh.
and you have 0.002 seconds.
Yes.
You have the 1 second.
Yes.
So you want to find how many times 0.002 is the 1.
Excellent. Okay, so let's answer that question first. So how many chunks of 0.002 seconds are there in 1 second? 500, right? Okay. Yes. So this chunk is 1/500th of 1 second. Right? That's what that little piece is right there. Okay? So then what? Yes.
In order to get from 0.002 to 1 second, you multiply by a factor of 500.
Okay.
So you do the same thing with the feet. You have 412, scale that up by a factor of 500.
Okay, so yes. But what do I draw? How can I represent where you're going? Yes.
You take 1/500th of the top bar.
1/500th of the top bar. Okay, so that's going to be like right there. What is that? Right. That's the 4,012 feet, right? This corresponds to 1/500th of total distance, right? Because that is the distance that corresponds to 0.002 seconds. Okay? So then we were going to scale up, right? There are 500 copies of 0.002 seconds in 1 second. So there should be 500 copies of 4,012 in the total distance. Yes, sir.
So why do time and distance have to be on separate bars? I mean, it kind of would make sense to have like one unit represents both 412 feet and 2,000 per second. So they could theoretically just be on the same bar. If they're always going to represent the same thing.
Sorry, hold on. I got incredibly distracted by weird buttons being pressed. So your question is, why can't you have feet and seconds on the same bar?
If one unit of each is always going to represent the same thing, and they're always so connected that like such that one unit of one is always going to represent a certain amount of the other. You can just have it so that one unit on the bar is 1,000 for the second and 2,006 feet.
So my answer to your question is that the theme of the course is to think about two quantities co-varying together. Okay, so in this instance, these quantities are fixed. Okay, we're talking about a set amount of distance, a set amount of time. But this way of thinking, approaching it as visualizing two quantities simultaneously, is going to lend itself into what we're about to do next. Okay, so that's why I'm emphasizing this approach. Your thinking is very solid in thinking, hey, these two quantities are related, right? We encapsulate their relationship in this thing called speed. Very solid thinking, and you want to hold on to that. But I also want you to be able to think about the two quantities individually, but in tandem. Okay? Okay. Alrighty. How are we feeling? Yes. Absolutely, and you should, right? Because so that is that's what we're actually computing here, right? So this is a multiplicative expression of what you just said, right? So we can capture 4,012 feet divided by 0.002 seconds. That gives us the speed, which as, what's your name? George. As George was just saying, right, that information is encoded in one quantity, what we're looking at here. Okay, so absolutely. So it's still division. Ultimately, what we still did was division. It looks like multiplication because of the funny fraction. Okay? Okey-dokes. All right. Get me out of here. Okay, so now what I want to do is do what I promised, right? I want to talk about how, or sort of give you the motivation now of why we've been concentrating on using 2 bars at a time to represent 2 quantities in one situation, okay? So I've got 2 bars here, and what I'm going to do is change the size of the blue bar, okay, so that it comes out to about, I don't know, here, okay? And I want you to tell me where the red bar will land, okay? So take a second to think about how you could figure that out. I'm going to write some letters, and you tell me whereabouts, which letter will the red bar shoot out to if I stretch the blue bar. You can confer with the neighbor. You guys have an idea? I don't know if your angle is very good. What's your prediction? E or F. Can you walk me through your reasoning? Okay. Okay, so your line of reasoning is to get from where it is now to the black mark, the blue bar will double in size. Maybe, I think it's probably a little more than that, but okay. So, but the line of reasoning goes, if the blue bar doubles in size, then the red bar should as well. What type of, what are you doing there? You're scaling. Excellent. Okay, so does it work? Let's see. Oh, I need to do this. Okay, so a little off, but that's okay.
Wow.
Okay. Oh, this was really cool, right? This is Graphing Calculator. You have this on your computer now. This is a neat program. Okay, and it's just the beginning. Okay, so so you gave me an explanation about scaling. You said if the blue bar doubles in size, then the red bar will double in size as well. I want a second explanation. Give me a different line of reasoning. Does somebody have one that they used? So how do I go from here to here using a different line of reasoning? You got one?
Yeah, I kind of use more for relative methods, so it's like the red bar will always be 3 times.
Okay. Yes. So the relative size argument, right? So the blue bar relative to the red bar is about 1/3-ish. Okay. So then if I make the blue bar grow, it will still be 1/3 relative to the red bar, right? That's a beautiful thing. Okay. Do you see the distinction in the arguments? Those are two distinct ways of reasoning about this, and I expect you to be able to do both. So should we recap, or do you get it? Recap? Okay, so one type of reasoning says, let me look at the individual bars. So if I look at the blue bar and the black mark, I'm going to slightly more than double the size of the blue bar to get to the black mark. So the red bar will slightly more than double in size to get to wherever it's going, okay? Versus focusing on the relative size of the blue bar to the red bar. So the blue bar is about 1/3 the size of the red bar. So when it grows, that new length will be about 1/3 the size of the new red bar. Okay? Two different ways of thinking about the same scenario. Okay? That was so good. Okay, so what can happen? I can just let this baby go, right? So no matter how big the blue bar gets, the red bar will maintain the same relationship, right? The same relative size. Okay, so I'm going to start doing some fancy things because this program is fancy. It's really cool. Okay, so I'm going to flip the blue bar to stand on the end of the red bar. Okay? So I'm going to animate this, and not yet though, because first I want you to predict what you're going to see. What will you see when I press animate? Okay, so take a second, think about it. Talk to your neighbor if you want to. All right, what are we going to see? Who hasn't talked yet? David, you haven't talked. What are we going to see?
Red bar will grow in size, and blue bar will also grow in size so that it maintains its relationship with the red bar.
Beautiful. Yes, right? So the red bar and the blue bar will both grow in size in a very specific fashion, right? They will maintain their relative size as they grow. Gosh, that was like, okay. Did anybody have a different answer? Now that I've already said that, that was awesome. Bad teaching. Okay, so yeah, right? Look at them grow. Super cool. Okay, so now, okay, let's get serious for a second. Have you ever seen something like this? Check this out. You've seen this, right? We're right next to an airport. Gosh, that's annoying. Okay, so what is this vapor trail showing? This is a vapor trail from an airplane, right? They make all kinds of cool designs. What is that vapor trail showing? Woohoo! Can I zoom? What is that showing? Yeah? Where the plane has been, right? It's keeping a record of every location that plane has been in for as long as that vapor is willing to display itself, right? So I want you to keep that in mind when I ask you the following questions, okay? So I'm going to embed this image now, our fun varying bars, okay? And I'm going to place it inside of some axes, okay? You have this program. Get excited. Okay, so let's say that maybe, I don't know, the x-axis is going to represent the volume of water in a bottle, okay? And we'll say that's in milliliters. And the y-axis is going to represent the height of the water inside of the bottle in centimeters. Okay? So then, given those two things, what does this point, oh, you know what, well, no, that's fine. What does that point represent? Okay. The height of the water relative to the volume in the bottle. That's what I just heard. Okay, so can we be really specific? We have axes. We have scales. So at 4 point, I don't know, we'll say that's about 4.4 and, I don't know, 1.1. Okay, so now give me more specific of a sentence. What does that point represent? Say it again.
4.4 milliliters is 1.1 centimeters tall.
We could be a little bit clearer because that confused me. So 4.4 milliliters is 1.1 centimeter tall. That's not a coherent sentence. I know you can do better. Let's see.
When the volume of water in the bottle is 4.4 milliliters, the height of water in the bottle is 1.1.
There we go. That's a coherent thought. I like it. So yes, what happens? What do I do? Escape. What happens if I move it? Can I do the same thing? Yeah. So now this point, what does that represent? Let's get some numbers in there. 7.6 or 7? I think it's slightly under 2. We'll go 1.9. I have closer line of sight. Okay, so again, what does that point represent? Give it to me in a sentence. A complete, coherent thought. Yes, ma'am.
When there's 7.7 milliliters of water in the bottle, the height of the water in the bottle is 1.9.
Beautiful. Okay, so when there are 7.7 milliliters of water in the bottle, the height of the water in the bottle is 1.9 centimeters. Okay, I have isolated 2 points. Are those the only 2 points that are being represented when I let these bars run with the wind? Right, when I go like this? What's happening? What could I be doing? If I were to keep track of every point, sort of like the airplane and his vapor trail, right? Then I can legitimately keep track of every point that can be represented by this relationship, okay? So, right, check this out. Flying backwards, flying forwards, okay? But the thing I want you to take away here is that this black line, right, not the red, not the blue, but the black line is what we traditionally describe as a graph, okay? What do I want you to take away from this? That line is nothing more than a collection, give it to me, of points, okay? That is a collection of points. It is not a straight piece of wire that you can bend, move around, flip over, and whatever. That is a collection of points representing a relationship between two quantities. That is huge, okay? That's what I want you to take away from this fun little airplane, okay? I hear zippers. Did I bore you? Are we okay? I still have 4 minutes, but actually, I'm pretty good. So that is where I wanted to end today. Look for your quiz on Tuesday on Blackboard. If you want to volunteer as a note taker, please come see me after class. I will give you directions. Oh, questions. Wait.
Just wanted to make sure that quiz is for us to do alone, and that can be done at any time.
Yep.
Time limit on it, or-
There's no time limit on it. You will take this test or the quiz on your own. It will be turned in on Friday. I will have detailed directions on Blackboard when I post it. Okay? Thank you, thank you.
I can do the note taking.
Cool. Okay, let me hopefully pause this recording device.